right, so let's take a look at our lesson for today. Our lesson is going to be on tangents, secants, and normals. So we're just now getting into derivatives, and these three concepts are pretty important. Let's start with our average rate of change. So average rate of change, many of you worked on this last year already and are familiar with it. It is the slope of the secant line, and this formula should look familiar to you. It's really just a slope, right? That's the formula for slope. It's the change in y over the change in x. So f of b minus f of a over b minus a. So let's take a look at an example of that. If you look right here, see the green line right here is our secant line. That's what, if you recall from geometry, remember a secant line is like a line or a chord that touches the figure in two places. So that's a secant line. And notice that here the green line is attached at A and B. So what we would do, the reason for this formula is perhaps we want an average rate, or maybe we don't have enough information to find the actual rate. Maybe we just want an average, or we can't find the actual. So here's what's happening. When I find the slope of the secant line, it's basically going to be the number or the average of all of the slopes all along here, slopes of tangent lines. If you can imagine a lot of little tangent lines being drawn here, finding all of those slopes, adding them up, dividing by how many there are, that's basically what this line is doing. It's calculating our average rate of change. So slope of the secant is average rate of change. Those words should be kind of cemented in your head, and they need to be attached to this formula. Certainly all the formulas up here are eligible for the formula quiz. Okay, so average rate of change. Now let's take a look at our two formulas for the derivative. This one, the vast majority of you have used quite a bit. We used it last year in Pre-Cal Pre-AP. You're familiar with it. This is called the definition of the derivative. So what do we use this particular formula for? We actually use it to find an equation. This formula finds an equation which can be used to find the slopes of the tangent lines. It's basically finding the equation of the derivative. That's what it's doing. It's finding the equation of the derivative, and I use that equation to find slopes of tangent lines. All right, so that is our definition of the derivative. So let's take a look at this tangent line. I would like to talk a little bit more about its significance. So if you look at this red function right here, this function has a derivative. The graph of it we don't see. We don't see the graph of the red one's derivative. What we're seeing, what the tangent line represents, basically the slope of the tangent line, what it is doing is it is the value of this red function's derivative at this point. And I'm going to say that one more time. The slope of this tangent line, whatever that number is, let's say it's 1. I don't know what it is. Let's say it's 1. This number 1 is the value of the red function's derivative at this point. That's what it is. So when I use this formula, this definition of the derivative, to find the equation of the derivative, so let's say we did that with this red function. I used this formula to find the equation of the derivative. I could use that equation, and I could actually find every single slope of every single tangent line on the function. That's what I could use it for. So that is our definition of the derivative. There's an alternate form of the definition of the derivative right here. This one we didn't use as much last year, so you may not be as familiar with it. I'm going to do an example with this one today, the alternative form of the definition of the derivative. So what do we use this one for? We use this one. This one is actually just going to find the slope at one location, the slope of one tangent line at C. I mean, that's all it's going to do. It's like a single-use formula. You use it for one thing, and then you really, you're done. You would have to use it again to get another value. So if you're going to need to get multiple values out of the derivative, you would want to find the actual equation. But if you just need one value, then this one is much easier and quicker to work with. Now I want to be real specific. I need you to know their names, which one is which. This one is the classic definition of the derivative, and this one is the alternative form of the definition of the derivative, because on the formula quiz I will ask you by name. And if you give me the wrong one, that's not going to be good for your formula quiz grade. Okay, you need to know which is which. This is the definition of the derivative. This is the alternative form of the definition of the derivative. Okay? And they're very important. I know some of you already know how to calculate derivatives, and that's great. We're going to learn all different kinds of ways to calculate derivatives, but the actual definition of the derivative and the alternative form are really important on the AP test. They're really important that we understand them, how to use them, and those kinds of things. So I completely understand it is a bit of a longer procedure than our rules that we're going to learn, but it is still necessary and important for us to be able to do both of these. All right, so that's just kind of a little update on that. All right, so we've talked about tangent lines, we've talked about secant lines. This normal line, so the normal line is, we don't use it that much in Calculus 1 and Calculus 2, but we do use it quite a bit in multivariable calculus, Calculus 3. So I'm going to introduce you to the concept of a normal line. You're going to figure out how to find it. But as far as using it, we're not going to really use it because we don't in Cal 1 and Cal 2. We do in Cal 3. So it's good. You need the foundation to know what a normal line is. So let's talk about it. So here's a picture of a normal line. The normal line is perpendicular to a tangent line at the point of tangency. So notice I have my normal line right here in red. I have my tangent line right here in black. Notice that they have this, you're seeing your right angle box. They are perpendicular at this point. That would be called the point of tangency. That's what a normal line is. So it's really like a definition for us, and you need to know how to find them, but that's basically all we're going to do with them in this course. So if you recall, basically when we have two lines that are perpendicular, recall their slopes. The product of their slopes is -1. Hopefully we remember that from Algebra 1. So that's what we're going to be using to find our equation of our normal line. Okay, are we okay with this so far? Any questions before we go to the example page? All right, let's take a look at this problem that we're going to work by using basically definition of the derivative. We're going to find the derivative using the definition of the derivative. Okay, great. So let's populate that formula. Let's see how we do that. So where the function, so this is function notation, so I'm sure y'all are familiar. This portion right here, I'm going to put where the x is. Okay, so the top right there is going to say the square root of 3 times x plus h plus 1. Okay, so that's this first piece, minus, and then the second piece is just the function itself, 3x plus 1. And that's all over h. All right. So when I plug a 0 in, I actually get 0 over 0. Okay, so that means that we have to keep going, right? We have to do something. It has radicals, so it'd probably be beneficial to multiply by a clever form of 1. All right, so we're going to multiply by 3 times x plus h plus 1 plus square root of 3x plus 1 all over the same thing, right? Because we can only multiply by the number 1. And this is looking a little bit crazy, right? Yeah, there's a lot going on. There's a lot going on, but it's going to clean up pretty quickly. So the nice thing about conjugates is that when we multiply them by themselves, the outside and inside, the foiling business, first, outside, inside, last, the outside and the inside go away. So I'm just doing first times first, which gives me 3 times x plus h plus 1. Outside, inside go away, then minus root 3x plus 1 times root 3x plus 1 is just 3x plus 1 all over h times that gigantic mess, 3 times x plus h plus 1 plus the square root of 3x plus 1. Okay, you're like, that's easier? It'll get better, it's fine. So I'm going to make combine like terms along the top, along the numerator. I'm just going to write it in a different color above here, just really to save some room. You certainly do not have to do it like this. You can keep writing. So we would distribute the 3 to the x and the h. So this would be 3x plus 3h plus 1. And then I distribute the negative, so minus 3x minus 1. All right, so that's what that simplifies or distributes to be. Now let's go ahead and I'm going to combine like terms. So the 3x minus 3x, those, go away, right? Those go away. So we're left with, well, and look, 1 minus 1, also goes away. So we're simply left with 3h. So we have 3h over h times square root of 3 times x plus h plus 1 plus 3x plus 1. Okay. Whew. Okay, we still have 0 over 0, but we have this advantage right here. Those h's are going to cross out. And what we're going to be left with, now let's take the limit, let's substitute in the 0. So I've got a 3 in the numerator, and in the denominator, I have the square root of 3 times now x. The h is 0. All right, we're putting a 0 in for h. All right, so that's taking the limit. Now let's do some simplification. So we've got, let's see, 3 times x is 3x. So I've got the square root of 3x. 3 times 0 is 0 plus 1 plus the square root of 3x plus 1, which gives me, so this is the result. That means the derivative is going to be 3 over, I have 1 root 3x plus 1 plus 1 root 3x plus 1. That gives me 2 root 3x plus 1s. And that's my derivative. Okay. Can't really see that, can we? Okay, so what it says is, if a ball is thrown into the air with a velocity of 40 feet per second, its height in feet after t seconds is given by, and so we have an equation there, y equals 40t minus 16t squared. And we're asked to do 4 different things here with that. They want us to find the average velocity for the time period beginning when t equals 2 and lasting 0.1 seconds. All right, so I'm looking at an x value, or this is in case of t value of 2. We're going from 2 to 2.1. Those are our t values that we're interested in. And to find the average velocity, we're going to be using that formula that we just looked at, f of b minus f of a over b minus a. So we have, this would be a and this would be b. We would simply take these numbers and substitute them in here to find f of a and f of b, which I did. I mean, I'm not going to go through the arithmetic, but I did that. So when you do that, when you substitute the 2.1 in, you get 13.44 minus, and then I substitute the 2 in, and I get 16 over 2.1 minus 2. Okay. And so then I do that arithmetic, and I get negative 25.6 feet per second. Okay, so let's talk about what that number means. That number is the average velocity for that time period. So velocity has, and we'll look at this, velocity has both speed and direction. So the speed that this ball is going is 25.6 feet per second. Since it's negative, the direction that it's going is down. So it's a ball, it's apparently already come up and is starting to come back down. So that's what this represents, our velocity, which is speed and direction. Speed, which you're probably, many of you are already familiar with all these concepts, probably have had physics or are in physics. So speed is how fast an object is going. It's the absolute value of velocity. So it doesn't have a direction, it's just a number. And displacement is the final position minus the beginning position. So if I'm standing right here and I walk all around the room and I come back here, my displacement is 0. Right? It doesn't matter how much distance I've gone, the displacement is 0. So there's just some concepts that we use in calculus as well as physics that we'll need to be aware of. Alright, so here we've found our average velocity. Now let's find the instantaneous velocity. And I'm going to use that, I guess, relatively new formula for you, or maybe not for all of you, our alternative form of the definition of the derivative. So let's write it up here. The limit as x approaches c of f of x minus f of c over x minus c. That's the formula. That's the one we're going to use on the second question, find the instantaneous velocity. Now, certainly I know, as I explained, I know that many of you already know how to do like the power rule and all that kind of stuff, but we're going to be working with these to get comfortable with them for just a little while, the definitions. Alright, so let's get our limit set up. So limit, instead of an x, they're using a t in this scenario, so I'm going to say as t goes to, and our interesting, the one we're interested in is 2. It says I need to put the function first. So the function is 40t minus 16t squared minus, then it says f of c. In other words, what I'm supposed to do is take the 2 and substitute it in here and get a value. I did that and I got 16. I got a positive 16, so minus 16 all over t minus 2. And that is the alternative form of the definition of the derivative. So what we're going to do is work through that and we're going to get an answer. Okay, so what I would do is factor that, and I'm not going to go through and show you the how I factored it. I'm just going to show you what the factor is. I mean, we all know how to factor in here. So limit t goes to 2. So it turned out to be negative 8 times 2t minus 1, and then times t minus 2 all over t minus 2. Okay, so we can see right there that we are able to cancel out the t minus 2's, and then I can simply substitute the 2 into my formula, or my limit, and get my answer. So I put a 2 in here, I get negative 8 times 4 minus 1, or negative 24. So negative 24, my units are feet per second. So that is my instantaneous velocity. In other words, that at the instant that t is 2, that's the velocity of the ball. Okay, at that exact moment. That's what instantaneous velocity means, at that exact moment. Okay? Equation of the tangent line. We get to use one of my favorite, actually my favorite equation of the line. I know, I do have a favorite equation of the line, and it is y minus y1 equals m times x minus x1. I love the point slope equation. When we find equations of a line, just substitute your numbers in there and leave it alone. Don't distribute, don't combine like terms, don't do any of that stuff. Just sub the numbers in and leave it alone. The more we mess with it, the more chance we have of making a mistake. So I advise against it. Just put the numbers in, leave it alone. Alright, our y1 and x1, well, we know that 2 is, well, the t value, not the x value, is 2. So how would I get the y value? I would take this 2 and I would put it up here in my equation and find the y value, which happens to be 16. Okay, so now I have my point, and now I have my slope. So now I just fill in my point slope equation of the line. So we have y minus 16 equals negative 24 times x minus 2. Oops, t. That's a t. T minus 2. And then we leave it alone. Okay? The last question asks us to find the equation of the normal line, which is really easy, right? It's at the exact same point as the tangent line. And all we have to do is change the slope to the opposite reciprocal. I mean, that's all there is to it. So the normal line is going to be y minus 16 equals, So the opposite of negative would be positive, and the reciprocal of 24 would be 1 over 24. So 1 over 24 t minus 2. Pretty easy, straightforward. I just need you to get comfortable with what a normal line is and how to find it.